Welcome to the video lecture for elastic potential energy. This will follow along in your textbook in chapter 10, section 3. We will look at a couple awesome examples, including bungee jumping, which is my next great adventure. It takes work to compress or stretch a spring. Work is a force times distance. So if we apply some average force over some displacement, in this case, for our elastic work that we're doing, it takes some initial force, and there's the final force that we're going to apply at the end over that stretch distance. Since it's going to be along the direction of the spring, the cosine is 0. This just becomes 1. The displacement is the change in position. The force, in either case, is just kx. Average force is initial force plus final force divided by 2. That's where we get the 1/2. And as we work through this, we come out with our work for elastic energy is equal to the potential of a spring initially minus the potential of a spring final. Normally, it's going to see this as potential energy of an elastic source is 1/2 kx squared. This is saying that the potential energy for a spring depends on the distance squared is proportional to the stretch distance, or the position, of the stretch distance squared multiplied by 1/2 the spring constant. When a spring is compressed or stretched, it has some elastic potential energy. The AP formula sheet has this as US, that's subscript S standing for spring, is equal to 1/2 kx squared. Your book is a little bit different. It does it as PE, elastic, or PE sometimes with a spring. Just a little different notation there. In class, we will use US, or you may see me get lazy and write UE, sub E, that's subscripts. Trampolines, excellent examples of conservation of energy. You are bouncing on a trampoline. Who doesn't like jumping on trampolines, by the way? I don't know anybody, unless somebody's has a bad knee. That would be the only situation they wouldn't like jumping on a trampoline. But jumping on a trampoline, you have some elastic potential energy. This becomes kinetic energy when you start moving. And as you go up in the air, or as this person on the trampoline who's very acrobatic is doing a flip, show off, they then gain potential energy as they move up. And in this case, rotational kinetic energy. So once again, we're back to conservation of energy. Energy is always conserved within a system. Maybe it's transferred into thermal energy or something else like that, but we will always have energy being conserved. Bungee jumping is pretty awesome. And it's kind of like the final frontier, but there's more than that. It's my next great adventure either way. So here we have an example of somebody bungee jumping off of either a bridge or a hotel or something like that. Their total energy is equal to their initial potential energy due to gravity. This is the initial height. As they fall further down, they get to a point where they reach a maximum speed. At this point, this is point A on here, they have a maximum speed. This would be their terminal velocity. Well, maybe not terminal velocity, but they'll be moving at their higher speed. Further on, at the same thing, at this point too, is when the cord will begin to stretch. And once the cord begins to stretch, it's going to start to slow the person down. So, as the cord stretches all the way down to point B, they lose kinetic energy, they gain elastic potential energy, and as they move all the way down to point B, at point B they have 0 kinetic energy. They still have some potential energy due to their height, but they have some potential energy due to the cord, or the elastic potential energy, or the spring potential energy in this case. On the next slide, I'm going to throw some more numbers in there, and I'm going to ask you to solve for some certain things. So make sure to take a moment right now and understand, maybe replay this and look back through to understand what is happening at each position. So for our problem tonight, Mr. Wolf goes bungee jumping. Mr. Wolf has a mass of 75 kilograms. I'd like you to tell me what his speed is at point A. I'd also like you to then tell him what his speed is at point B. This is where the cord is stretched to the maximum length. And finally, I'd like for you to calculate out what the spring constant for the cord is. Keep in mind that the change in position for the cord, it relates to the height, but it's not equal necessarily to the height. You're going to have to calculate that out individually. Remember also that the cord starts stretching at point A. So A is from between when he jumps to point A, he's in free fall, and at that point the cord or spring starts applying an upward force. Have a good night and see you tomorrow.